Okay, ladies and gentlemen, let's continue with Chapter 7. Chapter 7 is External Forced Convection. With the previous chapter, we've looked at the fundamentals of convection. Specifically, we've done a lot of fluid mechanics revision. And now, the practical applications are going to follow in the next 3 chapters, where we're going to look at external convection in Chapter 7, internal convection Chapter 8, and natural convection in Chapter 9. With all of these chapters, the fluid mechanics is part of convection. So for that reason, I'm going to very, very quickly, in all cases, just do a little bit of fluid mechanics revision, and then I'm going to put in the heat transfer part just to bring it into context. Okay, so what we're going to do specifically in Chapter 7, external forced convection, is we're going to look at drag and heat transfer in external flow, parallel flow over flat plates, flow across cylinders and spheres, and flow across tube banks. So if you just think of the geometries that we are looking at, we start with our simple case, always of the flat plate, then start making it more complicated, so from flat plate to cylinders and spheres, and then banks of them, so quite a few of them. And that is not at all representative of all the external forced convection applications which are available. There are many, many more. But the approach that we are going to follow here will also be valid for all the other geometries of importance. Okay, so let's start again by paragraph 7.1, drag and heat transfer, and just in terms of a little bit of fluid mechanics revision, remember the drag force, Fd, is equal to Cd, which is the drag coefficient, multiplied by half rho V squared multiplied by the area. And the area, now depending on the geometry, if it is this thing, and the flow would come in this direction, then it would be that projected area. If the flow would be from this direction, it would be that area. Okay. If it's a flat plate, like this piece of paper, it would be the surface. So the surface is always a very important thing in terms of which surface is being used, and that are usually connected with each other. So you have to go and look at the experiments. What does the experiment say? Which area should be used? Very, very important. Now this drag coefficient, CD, and the drag coefficient consists out of skin friction drag plus a component of the pressure drag. Okay. And I do not have time to do the revision of it. It is in the textbook. Just go and read through it again. It is very important that you at least know what are the different components and how do you get this total drag coefficient. In terms of heat transfer, okay, so if we do experiments, then as you can see and as we've discussed, the drag coefficient would be a function of, if we just look at this, of velocity, which is actually Reynolds number. So all the experiments and all the correlations would give us the drag coefficient as a function of Reynolds number. So CD is always a function of Reynolds number. Okay. In heat transfer, it's a little bit more complicated. Okay. So in heat transfer, we have the Nusselt number, and now it's a function of the Reynolds number and the Prandtl number. Okay. If there is no natural convection or buoyancy effects, if that is the case, then we still have another number, which is the Grashof number, which also needs to be taken into consideration, and that we will do in Chapter 9. Okay. Now, this is for average data. We have to remember that if we do measurements or experiments of CD, or the friction factors, whichever it is, as a function of length, okay, over the body. Let's suppose it is a flat plate. Then it is not a constant. Okay. If it's a flat plate and we do measurements on the flat plate, then it would differ from position to position because of the boundary layer, the velocity boundary layer as it develops. Okay. And the same with the Nusselt number or the heat transfer coefficient. Okay. So they are actually local values. But as engineers, we always, in many cases, or not always, but in many cases, we want the average values. Okay, so now before we get to the average values, we should also then remember that the Nusselt number, the local one, is a function also of position. Okay, of position of x, and then the Reynolds number, but take note, the Reynolds x. So the Reynolds number at the position where we take the measurement, and the Prandtl number. Okay, so it's a function of the Reynolds number at the position, and yes, it is true that in many cases we are interested in getting the average heat transfer coefficient and doing the integration so that we can get the average of the friction coefficients, because it's just so convenient for us to work with. Now in this, what is also important to realize is that if we have a geometry, again a flat plate or aeroplane wing or this thing, and there's heat transfer, then the temperature changes in the boundary layer. Okay. And or the surface temperature might also change. So the fluid properties of density, viscosity, thermal conductivity, quite a number of them, they are all functions of temperature. If the delta T's are low, then the functions are not that critical. If it's very large, then it can be quite large. But the agreement that we make, or agreement that has been made under many people that's doing these experiments, would be to say, let's define a film temperature which is always equal to the surface temperature and the free stream temperature divided by 2, and all the properties of viscosity, K, Cp, rho, etc. When we go and get them in the tables or whatever, we use it at that temperature. It just makes things more simpler, and if everybody does it, you know, then it's just simpler for everybody. Okay. Now, if we look at getting these averages, how do we get the average values? Well, the average values we need to get by integration. So if we want to get the average skin friction coefficient, then it is equal to 1 divided by L, integral from 0 to L of Cfx dx. Okay. So that equation, that local values of Cf, as it's varying there, we need to get the surface area underneath it divided by the length, and that would give us the average friction coefficient. And then obviously the same approach is being used for the heat transfer coefficient. It is 1 divided by L divided by the integral from 0 to L from the heat transfer coefficient dx. Okay, take note, these are the local values. Okay, so those are the local values, and these would then be the average values. Sometimes I actually prefer to do that, to indicate the average values and to make it more prominent. It is not the notation being used in the textbook. Sometimes I do it and sometimes I forget, but if you want to make it simpler for yourself, I would recommend that maybe you think of doing that. Okay. Right, paragraph 7.2 is parallel flow over a flat plate. So here's the flat plate again. We've done it in chapter 6. we've looked at the boundary layer, all the equations, the continuity equation, the momentum equation, the energy equation. We looked at how Blasius solved this problem for us so that we can actually determine the boundary layer thickness, okay, boundary layer thickness, and the CF value, and then also the Nusselt number, thermal boundary layer thickness, and how we can get the Nusselt number. Okay. Now, what we did was for laminar flow. Unfortunately, all the flow in real life is not laminar. Most of it is actually turbulent. Okay. So let's take that now into consideration and make things more general and put everything together. So again, just in terms of the notation for a flat plate, if that is a flat plate, and we have the case of the velocity and the temperature of the free stream flow, which can be a fluid or a gas. And this plate is now at a constant temperature Ts. And it has a length of L. Okay, that is its length, L. Okay. What happens is we know that there are laminar flow, the first part, okay? So that part is laminar. And we know there's an air and also a part of transition, okay? But what we do is, to make things simpler, is we are going to say, well, let's forget the transition part and we actually work it into the turbulent part, and we rather divide it into two separate areas. Okay, so the laminar flow regime and the turbulent flow regime. Okay. And where does the flow change from laminar to turbulent? That is very important, and that is that distance, and that is called the critical distance. Critical distance, XCR. And this critical distance, where the flow changes from laminar to turbulent, we can calculate it with the critical Reynolds number, where the critical Reynolds number is equal to rho VL divided by mu, or we can write it as the velocity divided by L divided by the kinematic viscosity, where the kinematic viscosity is just equal to the dynamic viscosity divided by the viscosity. Okay. Okay. So the critical Reynolds number, with that we can actually then calculate that distance. So just to, in terms of our general definition, this L now should actually be the velocity multiplied by the critical distance divided by the kinematic viscosity. Okay. So L would be the length where the Reynolds number changes from laminar to turbulent. And the critical Reynolds number is unfortunately not a simple thing. It's not a simple thing, although there is a value, and I'm going to give it to you just now. It is a function of lots of things. The surface geometry, okay, I'm just writing down SG, surface geometry, okay, so it's a function of the surface geometry. The roughness, the surface roughness, epsilon divided by L, surface roughness. Then also on the upstream velocity in terms of turbulence effects in the velocity. Okay, so although that velocity there, if we would measure velocity as a function of time, okay, with very, very sophisticated experiments, okay, then it might be a constant like that, smooth. On the instrumentation, the velocity is absolutely steady. Okay. But now, there's new instrumentation that can actually measure better. And if you would now do a measurement over smaller delta t and you actually open it up, then, you know, there might be a small fluctuation in it. Or you're busy in the lab and the whole train passes, there's vibrations, and that would, for that small split second, cause a small velocity fluctuation, and then it would actually changes the transitional behavior on the flat plate. So it's a very, very complicated thing. Okay, then it's also a function of the type of fluid. And with the type of fluid, it would obviously include all the properties, the density, the CP value, the viscosity, etc., and the thermal conductivity. And as I've said, any other upstream effects and vibrations. All of that influences the transition. But to make things simple in this course, what we're going to do is we are going to make the agreement that the critical Reynolds number for this module is equal to 1 multiplied by 10 to the 5th. Okay. Yep, there's a question there at the back. I beg your pardon, can you just...
Dynamic viscosity, shouldn't it be either new at the rank, or it should be different in the equation? In the critical Reynolds...
Oh, sorry, sorry, okay, so the question was just this kinematic viscosity, shouldn't it be the other way around? Yes, of course, thank you. Okay. Right, so the critical Reynolds number, our agreement in this module is that it should be 100,000. It can be up to about 3 million and more in industry, so there's a gray area. But in this module, what we're going to do is we're going to say, let's use 1 multiplied by 10 to the 5. Okay. Now, let's just go back to our previous chapter and take out some of the most important results that we're going to use, together with the results for turbulent flow, and then look at the average values. Okay. So, if we now look at friction coefficients. Okay, friction coefficients. For local and laminar flow. For local values and for laminar flow, the boundary layer thickness is equal to 4.91 multiplied by x to the Reynolds number, take note, local to the half. Okay, Reynolds x means the Reynolds number. If we want to work out the boundary layer thickness here, then we have to calculate the local Reynolds number, which will be rho v multiplied by that distance divided by the viscosity. Okay? And the CF value, the friction coefficient, which is then equal to 0.664 divided by Reynolds, 0.664 divided by Reynolds x to the half. Okay. So it would mean this is valid for a Reynolds number smaller than, okay, ladies and gentlemen, sorry, that one should be 5, okay, 500,000. Critical Reynolds number in this module, not 1 multiplied by 10 to the 5, but 5 multiplied by 10 to the 5, 500,000. Okay, so for laminar flow, those are the local values. Okay. For turbulent flow, again, take note, local values, local turbulent, then the boundary layer thickness is equal to 0.38 times x divided by Reynolds x to the 5th. And the local friction coefficient would be CFX is then equal to 0.059 divided by Reynolds x to the 5th. Okay. And because it is now turbulent flow, it would be valid for Reynolds numbers obviously larger than 500,000, but smaller than about 10 to the 7. Okay. If it's more than 10 to the 7, then there are other equations that you can use. Okay. Take note, local values. Again, what does it mean? It means that if we now go and look typically what happens with these values as a function of x, then, although not specifically described in these equations, if we would look at CF, okay, at the leading edge, what would happen with CF at the leading edge? What would the Reynolds number be at the leading edge? The leading edge there, the Reynolds number, rho v, not the critical one, but that is the Reynolds number. L is the distance from there. So L is equal to 0, so the Reynolds number is 0. Okay. So if that is equal to 0, then we see that theoretically the CF value at the leading edge is infinite. Okay. So it is infinite, and then typically it would come down like that, up to the point of transition. Okay. Now, although previously we've put everything there together, I'm just opening it up now again. So that is laminar, that's transition, and that is for turbulent flow. And then it would do something like that. Okay. So although my sketch is not that well, or not that good, although we've got this effect there, in practice if we do experiments, you know, it is more something like that. Okay. So we do not really get, obviously, that infinite high value at the leading edge, because it is just the mathematics that previously was not taken into consideration like that. Okay. So in general, that is CF. Okay. And I'm going to come back to this sketch a little bit later. It is very, very important. Right. Now, as engineers, you would look at this and you would say, oh, yeah, well, that is great that you give me these results to design with, but please give me the average ones. Okay. And depending on how critical it is, you can look this with the eye and you could say, oh, well, you know, it's approximately so many. Do just an integration with your eye, or you can do the integration yourself, many different ways to get the average value. Okay. How do we get the average values? As I've said previously before, if we look at this, we need to do the integration over the length of the local value. And that is exactly what we can do. So what we can do is we can say, well, let's look for laminar flow only. Okay. And we would say that the CF value is now the average value is equal to 1 divided by L over 1 divided by L CFX divided by dx. Okay. Okay, now just not to confuse us, let's just call this, let me rather go back to this one here, okay, because we've got the transition flow area there. Let's call that 0.0 and that 0.1, and maybe there 0.2. Okay, so that would be the laminar flow regime. Okay, so this would be for L from 0 to 1. L from 0 to 1. It would only be in the laminar flow regime that we do the integration now. So we would like to do the integration for that part there. Okay, what does it mean? It means we get the area, okay, and we divide it by this length here to get the average. And that is just normal integration. You can do that yourself. And if you do that, then you're going to find that CF, the average value, is equal to 1.33 divided by Reynolds, take note, L to the half. Okay, and this L, what L would it be? it would be over the laminar length, okay, which in this case now would be from 0 to 1. Okay. You agree? Understand? So just do the integration. Right. Now we can do for the turbulent part also. Okay, now there are two approaches. You can use the lazy approach or the theoretical correct approach. Okay. With the lazy approach, we're going to say, well, Achman, let's forget the laminar flow regime. We just look at the turbulent part. So let me rather use this sketch here. Forget about that and let's just do that part. Okay? And obviously we can have a discussion on is it correct or not. But it's going to depend on the application, and I'm going to show you some examples later on. So if we do the turbulent part only, and now the integration would then be from 1 divided by L, the length 1, 2. Okay, so it would be now over that length. Okay. The integration of the CF x dx part, and if we want to, we can actually call this equation 1 and that equation 2. Okay. And in this case, it was equation 1 that needs to be integrated, and in this case, it is equation 2 that needs to be integrated. Okay. And the result would then be equal to 0.074 divided by the Reynolds L to the 5th. Okay? And then we can do the other approach and say, well, this is not so, what you've done now is not so accurate. I mean, you can't really throw that away. And then you can say, oh, for heaven's sake, let's do that also. You can say, so the laminar included plus turbulent. Okay, and then we can say, well, let's then get the average of as 1 divided by the total length divided by the integral from 0 to L1 of CF x dx plus the integral from 0 L12 to L2 CF x dx, everything like that. And this is obviously again equation 1. And this part would be equation 2 in the integration. Okay, and what is going to help us in terms of where this position is the critical Reynolds number. Okay. Okay. And the result of that is that if we do then the integration, then the average would be equal to 0.074 divided by Reynolds L to the 5th minus 1742 divided by Reynolds number L. Okay. And now this equation would then be valid for Reynolds numbers larger than 5 multiplied by 10 to the 5 and typically smaller than 10 to the 7. Okay. So this approach can only be used if there is a laminar part in the equation, so, which means that the flow in general must be turbulent downstream. Now that is the equation for a very smooth plate. There's also equations for a rough plate. So if we have a rough surface, then CF would be equal to 1.89 multiplied minus 1.72 multiplied by the log of E divided by D to the minus 2.5, and E would be that surface roughness. Okay, that's now the fluid mechanics part. Now we have to do the same for the heat transfer part. Okay, for the heat transfer part again, there's going to be a local Nusselt number if the flow is laminar. There's going to be a local one for turbulent, and for each one of them we want the average values, and we would like the average for the two together. Okay, so let's look at the heat transfer. Okay. Right, now for local laminar. For local and laminar, yep.
So I was going to ask that rough surface CF, is there not another laminated turbulent region if there's a rough surface?
The question is there a laminar and turbulent regime if there's a rough surface? Unfortunately, it's not a simple answer. The laminar regime becomes smaller and smaller. So typically, if you just look at typically in a tube, the friction factor as a function of Reynolds number, you get something like that, okay, and that is the transition point, okay, and then you have all the other lines there of roughness, okay, and in the Moody chart you will see that area there is gray, okay. All our latest experiments are showing that actually this should be modified where the gray area actually does something like that. Okay. So which means that the rougher the surface is, the quicker the transition will occur from laminar flow to turbulent flow. Okay. So in general, this area, this would become shorter as the roughness actually increases. Okay. To answer your question? Okay. Right. Where were we? Heat transfer. Okay. Look at this. Local values. Okay. Now, the Nusselt number, because it is local, Nusselt X, okay, is then equal to the heat transfer coefficient, local X, multiplied by X divided by K, is now equal to 0.332 Reynolds X to the 0.5 and Prandtl to the third. Equation 3. Okay, and again, I'm not going to write it here. Again, I'm not going to write it, but if we just look quickly here, laminar flow, Reynolds numbers, smaller than 500,000. So this equation is valid if the Reynolds number is smaller than 500,000. Okay. Then for turbulent flow, local and turbulent, okay, then the local Nusselt number would be equal to 0.0296 multiplied by Reynolds X to the 0.8, Prandtl to the third, okay, and equation 4. This equation would now be valid for Reynolds numbers larger than 500,000 and smaller than 10 million. Okay, but there's another boundary condition, and that is that it is valid for typically Prandtl numbers larger than 0.6 and smaller than 60. It is in your textbook. I'm not going to write it out. So just take note, there are also some Prandtl number limitations on it, and if I have time, I'm going to address one of the Prandtl number limitations on this equation. Right, so if we look at these local values, okay, and we look at the fluid mechanics, we can see the similarities, okay. So if we would now go and plot the local heat transfer coefficients on the same graph, okay, on the same graph, then typically they would look the same. Okay. Take note, the scales are not the same, but the forms are exactly the same. Okay. So again, you're going to have on the leading edge, theoretically, should the local heat transfer coefficient should be infinite, then it decreases. In the transition, it increases, and from there on, typically something like that happens. But in general, in turbulent flow, the values are higher than for laminar flow. Okay. And what also connects them, okay, is the Prandtl number effect, where Prandtl to the third is approximately equal to the boundary layer thickness, which drives the local skin friction coefficient, and the turbulent boundary layer thickness, which drives the heat transfer coefficient. Okay, so the similarity there in terms of the Prandtl to the third is actually what is just changing the scales, but in general the forms are exactly the same. Right, so again, we need to do the integration. Okay, so we need to do the integrations. So if we now look at laminar flow, average. Okay, laminar flow average, which means that we have to take now the Nusselt number, okay, and do the integration, blah, 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 and the equation that is now going to be used in there would be equation 3. Okay, the local value for laminar flow that we do the integration for, and the result is that the Reynolds number is equal to 0.664 Reynolds to the 0.5 and Prandtl to the third. Okay, then the same for turbulent average. The Nusselt number, again I put that on to indicate it's the average value. If we do now the integration over the length, and now we use equation 4, the local Nusselt number equation, let's just look at it again here on the side of the board, equations 3 for laminar flow, equation 4 for turbulent flow. So if we take this equation, put it into that equation, actually determine the area underneath divided by the length. Okay, then the result is that the Nusselt number is equal to 0.037 multiplied by Reynolds to the 0.8 and Prandtl to the third. Right, and then the last part is then exactly the same as we did here. Okay, here we first look at the laminar part and the turbulent part, and then we've said, well, let's do it very theoretically correct. We do the integration from 0 to this length, and then from there to there. Okay. So let's call it turbulent. Taking into consideration the laminar regime results. Okay. And now we do it for the Nusselt number is 1 divided by L for firstly 0 to L12 plus L12 to L. Okay, so do the integration for both of them together, and then the result is that we get the equation which says it is equal to HL divided by K is equal to 0.037 multiplied by Reynolds to the 0.8 minus 871 divided by Prandtl to the third. Okay, an equation is valid for Prandtl numbers larger than 0.6, smaller than 60, and then for Reynolds numbers larger than 500,000 and smaller than 10 million. Then there's also an equation. Okay, take note, I've said that this equation is valid for Prandtl numbers smaller than 0.6, Prandtl numbers larger than 0.6 and smaller than 60. Right. Now what if we have Prandtl numbers which is not in that regime, typically like liquid metals, like mercury, metals, okay. It would have a high thermal conductivity, so it's typically been used in many nuclear reactors where we do not have a lot of surface area, and therefore we need something with a high K to get the heat out. Okay, so a high K, if you look at the Prandtl number is Cp multiplied by the viscosity divided by K. Okay. And that is then why the Prandtl number would be small. Okay. Because if the thermal conductivity is very, very high, the Prandtl number is very, very small. What does that mean in terms of the boundary layer theory that we've looked at in the previous chapter? It would mean that the velocity boundary layer would typically do something like that. Okay. And the thermal boundary layer would do that. Okay. Now, why would something with a very low Prandtl number, if we just look at these equations that we've looked at, the Nusselt number is always a function of Prandtl number, do you see? So in general, you would say, if I would like to have good heat transfer, select a fluid with a high Prandtl number. Do you agree? Makes sense. The equation tells you that. Okay. But if you think about it carefully, that remember there the thermal conductivity is coming in. So although you now calculate the Nusselt number, you're going to multiply, to get the heat transfer coefficient, you have to multiply with the thermal conductivity. So something with a high thermal conductivity is going to give you a high heat transfer coefficient. So you cannot just use the Nusselt number. Okay? The Nusselt number doesn't tell you enough. Remember, in the Nusselt number is the thermal conductivity. Okay. So the thing now with mercury would be a very, very good example. Many people would look at mercury and say, no, my Prandtl number is too small, take it out. I'm not going to consider it. Why would something like mercury be an excellent fluid to work with? Also, if we look at this, we will say that, no man, look at the thermal boundary layer, it is thick. Okay. It doesn't diffuse the heat very, very quickly. Okay. So why would we like to use mercury then? Can any one of you see it? Okay. If we think of this velocity, let's suppose it is 100 meters per second. Okay. Let's suppose the thermal boundary layer thickness were up to there. Okay. So it would mean that if the thermal boundary layer thickness is here, then the velocity should be much, much lower than 100 meters per second. You agree? Okay. Okay. But with that velocity, but at that one there, what does it mean there? At this position here, it means the velocity is equal to the free stream velocity. Okay. It's equal to the free stream velocity. So it is mixing that fluid very, very well. And for that reason, we get very, very high heat transfer for something like that. Okay, so there's also equations for liquid metals, and typically they are given as a function of the Peclet number, and the Nusselt number is then written something as 0.565 multiplied by the Peclet number. Okay, and the Peclet number, and in CFD you're also going to get to the Peclet number. It's a very important number. That is equal to the Reynolds number multiplied by the Prandtl number. So the Reynolds number multiplied by the Prandtl number is the Peclet number, and this equation would then be valid for Prandtl numbers smaller or equal to 0.05 and Peclet numbers larger than about 100. Right. Now that we know how to get the average heat transfer coefficients, people always like to look at exceptions. Oh, okay. Before we get to that, so what you can see is now we have two different equations, one for liquid metals, one for the rest, and then there are many more equations. So in your textbook, for example, there's an equation of Churchill and Ozone. Okay, Churchill and Ozone, which was developed in 1973, and it is equation 7.26. It's a little bit of a long equation, and that's why I'm not going to waste time to write it down. But with this equation, you can then also do liquid metals and the rest. So more average, more general equation. But, ladies and gentlemen, and I think that is one of the most important things that you need to take note of. If you look at this chapter and many of the chapters that's going to follow, there's going to be lots of equations. Okay. And then the problem is going to be in the test and exam, or with assignments, or when you want to work in industry, which equations should you use? Okay. Now the answer is in the fine print, like always. So with every equation, there's fine print. Read it very well and take note. Just as an example, for this equation 726 that I didn't write down now, it says it has been obtained for an isothermal surface. What does isothermal mean? The temperature is constant, but it could also be approximately be used for the case of a non-isothermal surface by assuming the surface temperature to be constant at some average value. So if you use the average, then it would also be fine. Also, the surfaces are assumed to be smooth, okay, and the free stream to be turbulent free. So there shouldn't be any turbulence in the free stream. And the effect of variable properties can be accounted for by evaluating all the properties at the film temperature. I'm not finished yet. I'm going to finish up in 1 minute. Okay. Now, there's another class of problem, and that is a problem where now we have a flat plate and the first part is not heated. Okay, so typically, if we can show it schematically, okay, we start heating the flat plate a little bit downstream. Okay, here's a distance here. See, where there's no heating, and what now happens is that the velocity boundary layer starts developing there. Okay, the velocity boundary layer. Okay, but the heating only starts here. So the thermal boundary layer would now start developing here. So like that. And although I've drawn it schematically like that, the Prandtl number is going to determine what is going to happen. So if the Prandtl number is very small, then the thermal boundary layer is going to do something like that. Okay? Okay. Now again, what you now can do is with the integration, you can take into consideration this first part, and there are also equations in the textbook in that regard. Any questions, ladies and gentlemen? If not, Thank you very much.